Support for Knowledge Stream comes in part from a generous contribution provided by an anonymous donor.
This is baseball season, as you know, and so this is an appropriate time for this talk. And I suspect there are a lot of Detroit Tiger fans in the audience, and you will recognize this, I hope, as Miguel Cabrera. And I find this video particularly interesting because you can, not necessarily because the bat broke, but because of the vibration of that bat after. It's the vibration that caused the bat to break to begin with, but you can really just see it freely vibrating right after that. So actually this was sort of a convenient trip to come here for me, because I actually piggybacked this on a trip to Michigan State. We were there a couple of days ago, and we arrived a little early, and we were looking for something to do, so we walked around the campus and noticed that there was a baseball game going on. So we went to the game, and by God, it was Toledo against Michigan State. And so there's a picture from the ball field, and if you look carefully at the scoreboard, at that point in the game, Toledo was ahead, 4-1. Turns out they actually lost, but all right, anyway. So, let me start off by sort of amusingly tell you a little bit about a connection between baseball and physics. So, Moe Berg. Has anyone here ever heard of Moe Berg? There is a very interesting book that I read maybe 20 years ago called The Catcher Was a Spy. So this is Moe Berg. His baseball card is another one of him. The Mysterious Life of Moe Berg. Moe Berg was a very smart guy. He was a Princeton grad. He spoke multiple languages. And he was also a baseball player. He was a journeyman catcher. He played in the major leagues for maybe 7 or 8 years. Never really made it into the starting lineup very much. But the really interesting thing about him is that he was a spy during for the United States during World War II. And actually one of his assignments was to attend this wartime physics conference in Switzerland, where Werner Heisenberg was going to be at this conference. So Werner Heisenberg is one of the founding fathers of quantum theory. He was also in charge of the Nazi nuclear bomb program. And Berg's assignment was to engage Heisenberg in some discussion and try to figure out how far along that bomb program was, and if it crossed some certain threshold, his job was to assassinate Heisenberg right on the spot. Well, okay, it never happened. But there is an interesting article that was in the New York Times in 1994 when Einstein met Berg. So the conversation went like this. Einstein says, "Mr. Berg, you teach me baseball, and I will teach you the theory of relativity." And then after a brief pause, Einstein goes on, "No, we must not. You will learn relativity faster than I will learn baseball." So baseball, you know, it's a complicated business, okay? Now, the way I got started with the physics of baseball is by reading this book. This is the third and probably final edition of the book, but the original edition came out way back in the early 90s. Bob Adair, he's got a Red Sox hat on there. He's a very old guy now. He's not involved with baseball so much anymore. But this is a brilliantly written book. There's something in there for everybody, whether your interest is primarily physics or whether it's primarily baseball or more or less anything in between. So some nice gems from there. And people often ask me, you know, are you trying to, what's the goal of this kind of research, physics of baseball? Well, the goal is not to reform the game, but to understand it. And a lot of physics is really just that. You know, you're not trying to have people behave differently or do things necessarily differently. You're just trying to understand what the players already have figured out intuitively, okay? How the game actually works. One of my favorite quotes is, "The physics of baseball ain't rocket science, it's much harder." You know, so it's not the physics of textbooks where you write down formulas and you solve equations and you make predictions. It's much more complicated. Life is more complicated than that. So the typical physicist approach to these things is you can't understand things from first principles, but you build a model. And then you do the experiment being the game itself. The physicist's model of the game has to fit the game. And that's the big observation, the big laboratory is the game itself. And so you try to fine-tune your model using data that you get from the game itself. Now, at the time Adair wrote this book, there were a lot of observations available, but nowadays the technology that's in every ballpark in Major League Baseball is such that things that Adair could only dream of doing when he wrote this book, you can do with far greater precision these days. And I'll try to give you a little bit of the flavor for that. There's another more advanced book. Rod Cross is an Australian of all things. He wrote The Physics of Baseball and Softball. Adair's book has, you go through the book, you'll hardly find a formula in it. This is loaded with formulas. This is a serious undertaking if you really want to read this book. But if you were a budding young scientist wanting to get involved in this field, this would be a really good starting place. And my own website is sort of a resource for the physics of baseball. This is Ted Williams here, and I'll show a little piece of the science of hitting later on in the talk. Okay, so this is what I'm going to talk about. So I got some cute little titles for these different sections of the talk. Get a grip, eyes wide shut, leaving the no spin zone, take me out of the ballpark, and extra innings if we get enough time, Rocky Mountain High. Okay, so I want to talk about this first part, get a grip. I want to talk about the physics of the ball-bat collision. So first of all, take a look. This is a high-speed video, 30,000 frames per second, of a ball that's fired out of a cannon at 120 miles an hour, and it strikes this steel plate. Notice how the ball gets crushed. You can see the same thing from this real picture of opportunity here. That was actually in our local newspaper in Champaign, where the ball and bat are in contact with each other. You see the ball gets crushed here. You see the ball wrapping itself around the bat. It's a lot going on. It's a very violent collision. It's also a very inefficient collision. So if you look at this one more time, look at the speed of the ball coming in, and then look at the speed of the ball going out. It's going a lot slower. It's going about half as fast. And that's because when that ball gets crushed, there's a lot going on. You know, if you were to dissect a baseball, you'd find that the inside is mostly wool yarn. Okay? Once you get that leather cover off, it's mostly wool yarn. And the fibers of that yarn are rubbing against each other, creating heat. And that heat represents energy that's lost to the ball. So the ball doesn't bounce very high. In fact, you could just take a baseball and bounce it off the floor, and you see it doesn't bounce very high compared with what you would get if you bounced the Super Bowl. Okay? So a baseball is very far from a Super Bowl. Okay, so a question I often get asked. So one of the latest buzzwords in Major League Baseball is exit velocity. By that they mean how fast does that ball come off the bat? So once you talk about that, then the natural question to ask is, what determines how fast that ball came off the bat? Okay? How much of it is determined by how fast the pitch is versus how fast the bat is being swung? So there's a very nice little formula that you can write down. Exit velocity is some number, Q, okay? This is, by the way, the only formula you'll see in this talk. Times the pitch speed plus 1 plus Q times the bat speed. So the bat speed, pitch, so the exit velocity is determined by pitch speed, bat speed, and this collision efficiency, which is a joint property of the ball and the bat. Okay? Now, this is not very helpful unless I tell you what Q is. Q is a fairly small number representing the fact that the collision is actually fairly inefficient. Okay? So Q is about 0.2. So you've got 0.2 multiplying the pitch speed, and you've got 1.2 multiplying the bat speed. So right away you can see that bat speed is far, far more important at determining the exit velocity than the pitch speed is. And you know, the announcers on TV oftentimes get this wrong. You know, it certainly is true that pitch speed matters, but bat speed matters much, much more. So if you put in these typical numbers and you put in 85 miles an hour for the pitch speed, now you say, well, 85 miles an hour, that seems awfully low, right? Well, a typical fastball in Major League Baseball is moving maybe 93, 94 miles an hour when it's released, but it's losing speed as it goes through the air. And by the time it gets to home plate, it's only going at 85 miles an hour. So that's what matters. That's what the bat sees, is the speed at the home plate. So that gives you 85 miles an hour. 70 miles an hour bat speed, multiply that by 1.2, do all the arithmetic, and you get about 101 miles an hour. If you look at data from Major League Baseball, you'll see that a ball hit at about that speed at about 25 to 30 degree launch angle will travel close to 400 feet, and this will get you a home run a fair fraction of the time. So these are sort of typical numbers. Each additional mile per hour of bat speed is worth about 6 extra feet on a long fly ball. Each mile per hour of pitch speed is worth only about 1 extra foot. So again, you see this factor of 6 difference in what matters. Okay, so what determines the exit velocity? It's these things. Okay, the collision efficiency depends basically on 2 different properties of the ball and the bat. It depends on the bounciness of the ball. That's the thing I was telling you about before. The fact this is not a particularly bouncy object. It's got a technical name. It's called the coefficient of restitution. And the bigger that coefficient of restitution, the more bouncy the ball is, the harder you can hit it. And nowadays, people who follow baseball know that the last few years there's been an increase in the number of home runs in Major League Baseball. And conspiracy theorists speculate that the reason for the increase in the number of home runs is that there's a conspiracy between Major League Baseball and Rawlings, the company that manufactures the baseball, to increase the coefficient of restitution without telling anyone about it. Maybe that's true, maybe that's not. Okay. The other thing that matters is the weight of the bat. And that sort of makes sense. I mean, you could swing you could take a wooden ruler and hit a ball, swing it at 70 miles an hour, you're not going to hit the ball very hard. But you take a lead brick and swing it at 70 miles an hour, you can hit the ball pretty hard. So it's the weight of the bat matters also. And the weight of the bat has to do with the fact that you really, to have a high collision efficiency, you really want a lot of mass behind that collision, okay? Okay, so I want to take a look at these videos. A lot of what you're going to see today is high-speed video. So here's a high-speed video, but look at the top one first. A batter is bunting the ball. So this bat has 0 bat speed, okay? And by the way, let me just going back to what matters more, pitch speed or bat speed. When you bunt the ball, okay, there's pitch speed but 0 bat speed. The ball's not going to go very far. Whereas consider the opposite extreme. You're hitting the ball off a tee, where there's 0 pitch speed, but you could hit the ball quite a long ways off a tee. So here's the first case where the bat is not moving at all prior to the ball hitting it. The ball bounces off of it, and look what happens to the bat. It recoils backwards, right? It's just like firing a rifle. Okay, the bullet goes off this way, the rifle recoils into your shoulder. Okay, it's a basic principle of physics. It's called conservation of momentum. The bat transfers momentum to the ball in this, to the left, and the ball has to transfer an equal amount of momentum to the bat to the right, so the bat recoils back. Now, when the bat is being swung, it doesn't recoil back because it's already moving forward, but it does slow down a lot. So this is a slow pitch softball, and there are 3 markers on the bat, and they're each being tracked probably at 1,000 frames per second. And look at the distance between each dot before the collision compared with after the collision, and you can see the bat slows down a lot, okay? And it slows down a lot. Again, it's this conservation of momentum thing. Okay. So for those of you who have had a course in physics, momentum is mass times velocity, okay? So and that's the mass of the bat that really matters here, okay? But consider the following. So here's my bat. It's the best I could do, sorry. The bat is being held by the batter, right? So the bat has a mass, but it's being held by the batter. How much does the batter's mass contribute to the mass of that enters into the collision? And so that's sort of an interesting question. How much does the batter's grip on the bat matter when that ball and bat are in contact with each other? It's an interesting question. Is there less recoil, or maybe said a little differently, does the bat slow down less if the batter has a tighter grip? Okay? Does the ball leave the bat faster? You get a higher exit velocity when the batter has a tighter grip. Does the batter muscle the ball? Okay? You hear announcers saying that a lot. Oh, he really muscled that ball. Okay? So here are 3 questions I'm asking, and then I'm going to tell you what a little story, and then I'll give you the answers to these questions. Okay. There are 2 key points to trying to answer these questions. One key point is that the bat is not a rigid object. Now, I don't have a real bat here, but actually in some sense this is even better. It's not rigid, it could bend, right? A wooden bat looks like it can't bend, okay? It's pretty stiff. You can't just hold it in your hands and easily bend it, but trust me, it can bend and you will see it bend, okay? So number 1, the bat is not a rigid object. Number 2, the collision between the ball and the bat is extremely rapid in time. It takes only probably less than 1,000th of a second. And those 2 factors enter into the answers to the questions that I just posed. Okay, so the bat is not rigid, it can vibrate. So let me show you some more high-speed video. Here is Marco Scudero back when he was playing for the Giants, and here he's hitting the ball off the so-called sweet spot of the bat. So the sweet spot of the bat is the place where you hit the ball that it gives you the highest exit velocity, it feels best in your hands, and it's because the bat is not vibrating. And you look, you see the bat slow down, okay, but it's a rather smooth, okay. The bat, you really can't see it vibrate. But now look at this. Here the ball is hit off the inside of the bat, and look at that vibration. The bat almost gets knocked out of the batter's hands, okay, and similarly on the outside of the bat. Look at that bat vibrate. The bat is not a rigid body, okay? Now, as I said, it's easy to show that with something like this, okay? But even with a wood bat, something that feels like it's sort of rigid. Now, anyone who's ever played the game knows that. You hit the ball on the sweet spot of the bat, you simply don't feel a thing in your hands. But you hit it off the sweet spot, either outside or inside, and it's vibrating and it stings. Okay? And if you get it vibrating, enough, it can actually break the bat. I was going to give you a demo, but I'll skip that. All right, so here is an example of a broken bat. The simplest vibration that the bat can undergo is one in which it's oscillating back and forth. So this point is moving up and down, but these 2 points here and here, where that black dot is, are fixed points. It's called a node of the vibration. And that point is basically the sweet spot of the bat. It's the place where if the ball impacts at that point, the bat doesn't vibrate. If the ball hits on the outside, as it does here, it starts to vibrate like this, with the handle of the bat initially moving towards the pitcher. And that's exactly how the bat breaks. And you see that in this video. You see the bat breaking, fracturing, bending towards the weak part of the bat, which is right in here, is bending initially towards the pitcher, and that's how the bat fractures. Compare that with this one where the ball hits on the inside, on the other side of this so-called node, and I'm going to have more to say about this picture later, and you see it bends towards the catcher and fractures that way. Okay, now we're getting to the key point here. The bat is not rigid. The collision between the ball and the bat is very fast. Here's what I want you to look at. This is actually sort of a very, very flexible bat that I got just to demonstrate the point I'm trying to make, and that's my hand here hitting with a ball the very end of the bat. What I want you to do is look at the top of the bat, where the batter's hands would be, and notice that the top of the bat does not move instantaneously when the bat is struck down here. It takes time, okay? You see there's a little rippling up the bat, okay? So you strike the bat at the barrel, the handle starts to move only after a noticeable delay. And you can really see it on this here. And what happens then? What happens is the bat, that little wave ripples up the bat. It bounces off whatever is at that end of the bat, whether it's just the knob or the batter's hands or whatever else is there, and then bounces back down again, okay? And it just sort of goes up and down the bat. After a while, it gets damped out and you can't see it anymore. But the key point now is this. By the time that reflected wave gets back to the impact point, the collision between the ball and the bat is already over. The ball has already left the bat. So if you think about it, nothing on the handle end of the bat could possibly matter as far as the ball is concerned, as far as the exit speed of the ball is concerned. Whatever is happening down here doesn't depend on anything that's going on up there, whether it's the knob or the handle, you know, how big the knob is, or in fact, the batter's grip, okay? In fact, if you think about if you carry that thinking to its logical conclusion, you would come up with the following statement. The batter could just as well drop the bat just prior to impact, and it would not make a bit of difference to what happens to the ball. You believe that? It is counterintuitive, but it is also true, okay? So, here's proof. Back in the 6 years ago, Memorial Day weekend, Todd Frazier, who was playing for the Reds at the time, hit a no-hands home run. So look at this. Look at this. By the time the bat and ball are in contact, the top hand is completely off the bat, and the bottom hand is just about to come off the bat. And this ball traveled something like 380 feet, and it was a home run. So providing real proof, in some sense, that the batter's grip had played no role at all in that collision. Okay? So let's answer these questions now. Is there less recoil with a tighter grip? No. Does the ball leave the bat faster? No. Does the batter muscle the ball? No. Okay. So now you've learned something. So next time you're listening on TV and the announcer, you know, the broadcaster says that he really muscled that, you're going to be there to contradict him. Okay, why is aluminum better? Okay. Well, aluminum bats are used, aluminum and composite material bats are used in amateur baseball. They're not allowed to be used in either major or minor league baseball. But in amateur baseball, they can be used, and it's the bat of choice. Now, an aluminum bat is actually a hollow object, unlike a wood bat. Wood bat is a solid piece of wood. But because the aluminum bat is hollow, this thing is hollow, okay? You know, with a solid, so you suppose you just had two bats that had exactly the same shape, same length, same weight, and the same profile, okay? Same diameter barrel. The wood bat would be more top-heavy, would have a larger concentration of the weight of the bat in the barrel of the bat than the aluminum bat, because the aluminum bat is hollow, okay? Aluminum bat has a much more evenly distributed weight distribution. So for an aluminum bat, it's because there's less weight out here, you can actually swing it faster, and that would appear to be an advantage for the aluminum bat. However, there's less weight in the barrel, and therefore the collision is going to be less efficient. And those two things are sort of a net wash, okay? So that mass distribution, the fact that the mass distribution for aluminum bat is more uniform, really doesn't play a significant role in getting a higher exit speed. So what does play the role? What does play the role is what is popularly called the trampoline effect. And the trampoline effect is the, so I have to give you a quiz. So any tennis players here? A few tennis players? So I'll start you out with the quiz then. To get, if you're serving the ball and you want to get a higher speed on the serve, do you want, and you have these three options. The strings don't matter is one option. Tighten the strings or loosen the strings. Okay, how many think you tighten the strings? How many think you loosen the strings? How many of those who are the tennis players, just tennis players, how many think you tighten the strings? How many think you loosen the strings? Okay, all right, so we'll get to the answer in a second. Okay, so here, I showed you this picture already. I turned it upside down for, I'm not sure why, but this is the ball hitting the steel plates, but it's going to the right this time, and you see it's upside down. So when the ball hits something solid like the steel plate over there or a wood bat, all of that energy goes into compressing that ball. Okay, you can see it. You could think of it as like a spring compressing and then expanding back out again. And as we've said already, that's a very, very inefficient process. Or the technical name for it is the coefficient of restitution is too small. There's a lot of energy lost. But when the ball hits a hollow bat, so here's a hollow bat, the hollow bat itself can compress. The wall of that bat can compress. You could also show it with a water bottle here. I can do it like this, okay? And some of the energy, instead of compressing the ball, goes into compressing the wall of the bat. And for interesting physics reasons, the energy that goes into compressing the bat actually is very efficiently returned back to the ball again. Whereas the energy that's lost due to compressing the ball just turns into heat and is useless energy at that point, okay? And that is what is known as the trampoline effect. What happens is then less energy goes into compressing the ball, and therefore less energy is lost. So you get a bigger bounce. So one way the reason why it's called a trampoline effect, imagine jumping up and down on the ground compared with jumping up and down on a trampoline. Okay, you know you can bounce a lot higher. So that's a trampoline effect. You can think of it as two springs mutually compressing each other. And so people talk about, instead of the coefficient of restitution, people talk about the ball bat coefficient of restitution because the bat matters also, hence the name BB core. And for those of you who play high school or college baseball, BB core bats are bats that have this quantity, the ball bat coefficient of restitution, regulated so it's not too high, so it doesn't perform too much better than wood. But in general, left to its own devices, a bat company can produce a bat that performs much, much better than wood. And so the answer to the question is you want to loosen the strings, because the more you loosen the strings, the more the strings can compress when the ball hits it, or in the case of a bat, the more this can compress. The wall can compress, and the more that happens, the bigger that trampoline effect is. Now, trampoline effects also occur in golf. So, you know, a wood in golf these days, any golfers here? No golfers? Oh, some golf. You know, a wood is not a wood. Back in the old days, a wood was made out of wood. Wood is not wood anymore, right? It's a hollow piece of metal with a thin plate over it. And that thin plate compresses. It's a trampoline. It's exactly the same effect. It's a trampoline effect. So, you know, what's the net effect of a trampoline effect? In golf, you got to make the golf course bigger in order to, you know, keep the scores reasonable. Okay, loosen the strings is the answer. Okay, second topic, eyes wide shut. Ted Williams. You mentioned Ted Williams already. Hitting is 50% above the shoulders. Probably even more, actually. And by the way, I'm also a big sports memorabilia / baseball card collector, so this is from my personal collection, 1955 set of Topps cards. Okay, this is too busy. I'm not going to talk. So I want to, well, let me go back. This is a very busy slide that Adair actually talked about in his book. Don't try to read what's on the slide. I'm just going to explain it to you. The question is this. Pitcher releases the ball. It takes, let's say, 400 to 450 milliseconds, 0.4 to 0.5 seconds from release to home plate. The batter observes the ball coming in, makes a decision, is he going to swing or not, and then suppose he decides to swing, then he swings. What's the timing of all that? Well, actually, if you work backwards, a typical swing in Major League Baseball from start, when you actually start to move the bat, to contact is about 150 milliseconds. So of that let's say 400 milliseconds, 150 milliseconds is taken up just by the swing. But there's also the time needed to process the information. The batter sees something, that information has to go to the brain has to process it, has to send a signal to the rest of the body to start swinging the bat. All that takes time. The bottom line is something like the following. The amount of time that the batter has, useful time to actually observe the pitch and formulate his decision, is only about maybe 200 milliseconds, not 400 milliseconds. Okay, so that's what this complicated looking slide is all about. Now this was, Adair talked about this at a conference that he and I were at together way back in the year 2000, and then he eventually wrote it up in an article. And this is actually appeared in the New York Times. But Adair did this based on his own understanding of things, his observations, but it was largely theoretical. But there was an experiment done by a Japanese group, and this is it. It's a very technical paper, so I don't suggest you try to go read it, but I'm going to give you the highlights of it. That actually is testing this theory. So I want to tell you about this experiment. As an experimentalist myself, I used to do experimental nuclear physics before I started doing baseball. You look at someone come up with a cute experiment like that, and your first thought is, gosh, I wish I would have thought of that myself. It really is cute. So you watch what I'm about to show you, tell me if you think it's cute too. All right, here's the experiment. So they took a bunch of batters. I think they were amateur. This is all in Japan. They were elite amateur players in Japanese baseball. And they were hitting pitches out of a pitching machine, which was programmed to throw fastballs and curveballs, but randomly, so the batter didn't know which pitch was coming. And here's the key point. Every batter was fitted with special glasses, with liquid crystal glasses, that with so-called electronic shutters, but whereby wirelessly you could actually close the shutters or open them at will. Okay, so the experimenters had the ability to essentially make the batter blind. Okay, all right. The batters were instructed to hit. There were 3 different conditions. There was what I call the no condition, where the shutter was open for the full trajectory. There was the release R plus 150, where the shutter was closed 150 milliseconds after the ball was released, and then the rest of the pitch was not visible to the batter. And then there was the A minus 150, where the shutter was closed 150 milliseconds prior to arrival. So the last 150 milliseconds was blinded to the batter. And the idea was that the experimenters, using high-speed video, recorded where on the barrel of the bat the ball impacted with the batter swinging. So here is a typical picture. The target, right in the middle, this is roughly the sweet spot, and you're trying to hit it, sort of in the center. You'll see that it ends up hitting a little bit above center, because typically that's really what you want to do, is because you want to get a little backspin on the ball. But high-speed cameras recorded the location impact on the bat with the goal of hitting on the sweet spot. Okay? So here is two typical trajectories, okay, that look pretty much alike right up until this point, and then they start to separate. So if the whole trajectory was viewed, you see the whole thing. Okay? The R plus 150, so this is 150 milliseconds, and then from 150 milliseconds on, the batter couldn't see anything. And this is A minus 150, the last 150 milliseconds the batter couldn't see. So those 3 different conditions. Okay, so now let's take a look. Here is the no condition, where the batter sees the full pitch, and this is where the balls were distributed along the surface of the bat. So it's all, they're near the sweet spot, a little bit high. As I said, you're usually trying to hit a little bit on the underside of the ball. Okay. Compare that with the R plus 150. That's this picture here, where the shutter is closed 150 milliseconds after release, and it's all over the place. Compare this with this, okay? They really don't look much alike at all. So the batter loses a lot if you're only looking at the first 150 milliseconds of the pitch. The batter loses a lot. But if you're looking at all except for the last 150 milliseconds, you know, that's basically the amount of time it takes to swing the bat. This and this look pretty much alike. They really don't look all that different from each other. Okay? So that this, in a sense, proves, or goes in the way of proving, that that last 150 milliseconds provided no useful information to the batter. And more or less confirms what Adair was saying. The last 150 milliseconds provides no useful information. What Adair hypothesized way back in 2000 is basically confirmed, and the batter could just as well close his eyes for that last 150 milliseconds. So there you go. Isn't that a cute experiment? I think it is. Oh, so here's Mariano Rivera, retired a bunch of years ago now, but he was probably the greatest closer in the history of baseball. Comes into the ninth inning and shuts them down. So here is a trajectory of his famous cut fastball as thrown to a left-handed batter. So it's the a solid red line here. And this is the last 150 milliseconds. If the ball were to travel right on a straight line, it would end up here. But the ball traveled there. And the point is, the last 150, prior to the last 150 milliseconds, those two pitches are not very distinguishable. You really have to go further along. So if the batter is in, you know, if nothing in the last 150 milliseconds is able to be processed by the batter, then the batter is really not going to be easily able to distinguish this pitch from this pitch. So here is a bat, and whoops, and you can see the actual pitch would have hit more or less on the label of the bat, quite likely would have broken the bat. In fact, Mariano Rivera was famous for breaking a lot of left-handed hitters' bats, as opposed to hitting it more or less on the sweet spot. Now, let's see, do I have this video here? Oh, there it is. This is Jake Arrieta, Cubs, sorry. I'm not a Cub fan, but whoops. Let me see if I can do this again. Oh. All right, sometimes this works and sometimes it doesn't. Let me go back and let me go forward again. He's throwing his fastball and his cutter. Okay, you had to look quick. The cutter broke into the left-handed hitter, the fastball broke away. And those two pitches, again, they were virtually indistinguishable, you know, certainly over the first half of the pitch. So that, you know, this is part of what pitchers do. They're trying to deceive batters. They're trying to make their pitches all look alike for as much of the trajectory as possible. For, again, the very reason that this experiment was about, that the last, you know, if they begin to separate in that last 150 milliseconds, the batter's not really going to be able to react to that. Oh, there we go. All right. All right, so summary of what I've done so far in this bizarre world of physics, the outcome of the pitch is not affected if the batter drops the bat and closes his eyes. So how weird is that? All right. All right, leaving the no spin zone, I want to talk about the spin of a batted ball. So this is something that occurred during the NLCS in 2016. The Dodgers, Chris Bryant was batting, and Jock Peterson is a center fielder for the Dodgers. And I want you to watch what he does here. He turns one way, turns the other way. Basically, he made a 360 and he missed the ball, and Chris Bryant got a double. So watch it one more time and see if you can figure out what he's doing. He really couldn't make up his mind which way to turn. So he really didn't know what that ball was doing. So this all has to do with the spin of a batted ball. All right, so then here's another famous play from the 2012 NLCS, Game 7. The Giants, Hunter Pence for the Giants. Pete Kozma is the shortstop for the Cardinals. Okay, and so notice Kozma breaks initially to the right and the ball goes to his left. He broke the wrong way. Okay, so I want to talk about both of these things and why the fielder did what he did and why he was wrong. Okay. In both cases, the fielder broke the wrong way, broke one way, and the ball broke the other way. The question is why. So there are two physics issues involved here, both of which have interested me for a long time. How does spin, the fact that the ball is spinning, affect the flight of the ball, number one? And how does the batter put spin on the ball? Okay? Batter puts spin on the ball, and that spin affects the flight, and that played a key role in both of these situations. All right, so I have to tell you very quickly about the aerodynamics of a baseball. So a ball's going through the air, like so. I'll do it this way, like that. Okay, and it experiences three forces on it. So if the ball didn't experience any forces, it would just go on a straight line. That's what physics tells us. But there are forces, the most common of which is gravity. It's pulling it down. What goes up must come down, okay? So the ball's going this way. Air drag is slowing the ball down. So air drag always acts opposite to the direction of the ball, and it slows the ball down. Air drag plays a huge role in baseball, okay? Without air drag, a ball that traveled 400 feet might travel 700 feet. So it plays a huge role. And then there is the so-called Magnus force on a spinning baseball. So in this case, the ball is spinning with backspin, and it experiences a force that's mostly up but slightly backwards because the ball is tilted a little bit there. Okay? Gravity is pulling it down. Drag reduces the speed. It doesn't change the direction. It just changes the speed of the ball. And the Magnus force changes the direction without changing the speed. It always acts perpendicular to the direction the ball is moving. And if you want to know which way a ball is going to swerve based on this Magnus force, you look at the leading edge of the ball. So you could either look at that or just look at this. If the ball is coming at you, whichever way the leading edge, the ledge that you see, is turning, that's the direction of movement. So a ball that has backspin has an upward deflection, topspin has a downward deflection. If it's spinning like this, it'll break that way. If it's spinning like this, it'll break that way. And you could rotate these axes and have it go up and in or down and out or all kinds of things. And that's part of a pitcher's repertoire, is learning how to control that spin axis to make it do what you want it to do. Keeping in mind that gravity is also acting on it. So whatever you're doing, the ball is always going to fall anyway because of gravity. Okay. So here's a series of experiments that I did a few years ago. I just wanted to show you this. This is kind of neat. Shows you how an experimental physicist works. We fire a ball at 120 miles an hour out of a high-speed cannon, and it's hitting this cylinder, which is my pseudo bat. It's just a wooden cylinder that I've got nailed down so it doesn't move. And the ball is hitting the top of the cylinder, so it bounces up. And notice the ball initially has no spin, and when it bounces, it has backspin. And in this experiment, I looked at these little dots that I had reflective markers that the whole idea was to try to quantify how the batted ball spin depended on the angle and things like that. Okay, so you can use that to develop a model for what's going on with the ball-bat collision. And it's friction that does it, but you don't need to know anything about that. However, the spin of a batted ball has results that if you just watch a game long enough, you'll see all the time. So for example, balls hit to either left field or right field tend to swerve towards the foul line. Invariably, swerve towards the foul line. Not invariably. In fact, there are some exceptions, and that's the exceptions I want to talk about. Balls that are hit with topspin oftentimes have tricky bounces in the infield. Backspin keeps the ball in the air longer. One of the goals of batters who are trying to hit home runs is to put backspin on the ball, because then the Magnus force is up, opposing gravity. Gravity is trying to pull it down, so the ball stays in the air longer so it can travel farther. And you can come up with all kinds of tricky pop-ups in the infield where the ball is spinning like crazy and the ball is, one very cute thing you could watch for also is pop-ups behind home plate. Those balls, so in fact, I'll get to that in a second. So here's Marco Scudero again. We've already seen this. Here's a ball that's hit more or less head on, and the ball goes out close to the direction it came in with very little spin on it. But here's a ball that's severely undercut, and it goes straight up with a lot of backspin on it. If you look carefully, you can see that spinning like crazy. So when the ball is hit, say, in back of the catcher, high up with a lot of backspin on it, so it's hit with backspin, so it's going like this. So the leading edge of the ball is the top of the ball because it's going up, and it's pointing back, it's turning backwards. So the ball is moving away from the catcher while it's on its way up. But now it starts to come down, it's still spinning in the same direction, the leading edge is down here, and it's now going towards the pitcher. And catchers from a young age are taught, don't overcommit on these pop-ups behind home plate, because you start running this way because the ball is curving that way, but then all of a sudden you found you have to back up at the last minute. You also see funny things like that happen in the infield. It's kind of cute. I call those paradoxical pop-ups. Okay, and so here is a ball that's hit. The bat is hit on top of the ball, so it's causing topspin. The ball goes down, and you see it's rolling with topspin. And again, balls hit line drives, especially line drives, hit to the left or to the right, curve towards the foul line. Okay, and here is Xander Bogaerts from the 2013 ALCS. You remember that one? He remembers that one. The ball is curving towards the foul line. You can see that on there. Okay, so here is back to Hunter Pence again. This is the one where Pete Kozma broke left and then he broke right. So fly balls towards the foul line, but not this one. Why? What was different about this? So let me show you what was different about this. It turns out that this was a highly unusual batted ball. Here is this batted ball. Notice the bat broke. Notice he almost gets impaled with a piece of shard of wood. And notice that the bat hits the ball 3 different times. Okay? 1, 2, 3. And because of the unusual nature of that ball-bat collision, if you look really carefully, you see when the ball comes off the bat, it's not spinning. So if third base is over here, first base is over here, it's not spinning like this, which would move it, break it towards the foul line. It's spinning in the exact opposite direction. And Pete Kozma, being a smart shortstop, knows that balls hit that way, is going to break to his right, but it didn't, okay? Because he couldn't see what we could see, okay? So he anticipated what it was going to do, but he guessed wrong. And so here it is. So this is sort of my estimate of what actually happened. Marco Scudo was standing about where this triangle is. He thought the ball was going to end up there, and ended up over there. And the ball ended up in the outfield. Hunter Pence, the bases were loaded at the time, okay? Pence ended up on second base, and I call this the triple-double. Triple because the ball hit the bat 3 times. Bat hit the ball 3 times, and double because he done it. Double cleared the bases. This was Game 7, and virtually that was the end of it. I mean, the Cardinals couldn't catch up after that, and the Giants went on to win the series and then the World Series. Okay, so there was the ball should have broken about 4 feet to. He expected it to break 4 feet to his right. It actually broke about 4 feet to his left. All right, what about the Jock Peterson, Chris Bryant, Jock Peterson? This is a ball hit directly to center field. Now, balls hit to center field, normally you wouldn't think would have any side spin on them. You should have backspin on them because you're hitting slightly under it, but it had slicing behavior. So this was hit by a right-handed batter. If you look carefully, this is a blow-up. It started out going slightly to the left field side of center field, and then it broke like this. So again, this is an exaggerated plot, but this is more of a normal plot of what actually happened. Why did the ball slice? The key to that is that the bat, when it hit the ball, was tilted downward. In fact, that oftentimes happens. I mean, you know, the strike zone is down here, the bat is up here, the batter's hands are up here. It's quite often that the bat is tilted downward when it hits the ball, okay? If the ball would have had would have been level, it would have come off the bat going towards center field with pure backspin on it. But just take that whole picture and just tilt it like this. Whoops. Here we go. tilt it like this, and you see it's got a side spin component on it too. And the direction of that side spin component is such as to make the ball slice. So off a right-handed hitter, it breaks towards right field. Off a left-handed hitter, it breaks towards left field. And experienced outfielders know this. In fact, if you look at how outfielders position themselves, center fielders especially position themselves, very often you see that center fielders are playing slightly to the opposite field off batters, knowing that the ball is going to slice. So Jock Peterson should have known it. He probably knows it, but he misplayed it anyway. Okay, Science of Hitting. That's the book he referred to. Let's see now. I'm gonna take maybe 10 more minutes. Will that work? Okay. So here's Ted Williams. He wrote the book, The Science, literally wrote the book on the subject, right? And here he is doing whatever he's doing. All right, so I want to take a few minutes to explain this picture here. So nowadays in Major League Baseball, there is this so-called StatCast system. Partly it's a Doppler radar system. If you go in any Major League stadium and look behind home plate up, maybe near the press box, and you see this big thing that looks like a widescreen TV, probably black. And that's a radar system. That's bouncing radar off the ball. It's used to track the ball, the pitch ball, the batted ball. So it measures things like the exit velocity. It measures the launch angle, measures the direction, tells you how far the ball went, how much it's spinning, tells you everything, okay? And so when you have that information, there's an awful lot of analysis you can do. So I want to tell you about this picture here. What I'm plotting here, this is sort of a heat map. So on the vertical axis, I'm plotting exit speed. So high exit speed, 110 miles an hour, low exit speed, 60 miles an hour, versus launch angle, 0 degrees, 10 degrees. So 0 degrees is coming out like this, 10 degrees, 20, 30, et cetera, or could go down, minus 10 degrees, okay? And red means the high on-base percentage, blue means low on-base percentage. So now you can look, what constitutes a well-hit ball? Okay, these are data from the 2015 season. What constitutes a well-hit ball? Well, you sort of see there are two regions here. There is this and there is this. So let's talk about both of these. So let's talk about this first. This is basically a line drive, typically a single. So it's a ball that's hit hard, so over 95 miles an hour or so, at a low launch angle. Okay, it's hit maybe 10 to 15 degrees. And you think about it, a ball that's hit hard, and it doesn't even have to be all that hard, but 10 to 15 degrees will get you over the infield, but it's not so high that the outfielder can catch up with it. So it falls between the infield and the outfield. That'll get you on base virtually 100% of the time. If you could always do this, you would always get on base, okay? This, if you now hit the ball hard still, but now at a somewhat more elevated angle, like 25 to 30 degrees or 20 to 35, some region like that, then that ball is going to go a long ways. And you're going to get a home run or maybe a double off the wall or something, a double or triple in the gap. So that's that region. This region is sort of interesting. It's balls that are actually hit weakly, yet manage to be hits. So imagine that you hit the ball a little blooper that goes over the infield, okay, at a reasonable launch angle, 20, 25 degrees, but not hit very high. You don't want to hit it hard, because if you hit it hard, then you're going to end up in the donut hole. You're going to end up here. So these are balls that are hit too hard to be just bloopers that fall in front of the outfielder. They're going to be lazy 300-foot fly balls. Okay, that's what we call the donut hole. And you can see the same thing here. And here's another picture of the, I want to show you this donut hole. So this is actual data, batting average versus exit velocity, 60, 70, 80, 90, 100 miles an hour, for 20 to 24 degree launch angle. So it's right along this strip here. If you hit the ball weakly, you get on base. If you hit it hard, you get on base. And intermediate, you're not going to get on base. And if you look at typical trajectories, that you can sort of see it here. When you're in this hole, in the donut hole here, the ball is traveling like 300 feet or so, and that's going to get caught. Can of corn, as they say. All right. So possible hitting strategies. The question is, knowing all this, okay, if you know all this, if you're a batter and you know all this, and they all do, I mean, they know it intuitively, they may not look at these kinds of plots like this. How do you adjust your swing in order to optimize whatever outcome you're trying to get? So if your goal is to get on base, you're not interested in extra bases, but you just want to get on base, clearly you want to hit the ball hard and hit it at some fairly small launch angle. And if your goal is to hit a home run or an extra base hit, you want to hit it hard, 25 to 30 degrees or so. And if you're trying to minimize timing errors, you want to swing level. Level in the sense that the ball is coming in, the pitched ball is arriving on a downward angle, and if you swing at the comparable upward angle, then that minimizes the kind of timing errors that you can get. That is exactly what Williams talked about in his Science of Hitting book. So he was a big proponent of that. So let me skip this. Let me skip all this. I'm going to skip all this. And I do want to show you a couple of things, though. Forget about this, because you can really understand what I'm about to show you by just looking at this plot here. So the question is, what kind of swing plane does a batter have? And the reason why this is important these days is largely because people are talking about it a lot. So one of the reasons people have speculated for the big increase in home runs is that batters are trying to elevate that ball more. They're ignoring the 10 to 15 degrees, well, that'll get you a single, instead are going for the fences. Okay? They're simply trying to hit more home runs. One of the reasons why that is a better strategy these days is because one of the other things that's going on in Major League Baseball these days is all sorts of strange shifting of the infield. And where a left-handed hitter, the second baseman, might be playing way out on the outfield grass. And that strategy of hitting at 10 to 15 degrees is more or less taken away, because for the second baseman can easily field that and throw you out. So if you take away that hit, what are you left with? You might as well go for the fences. And the way you go for the fences is by elevating your swing. And the way, so you increase your swing plane. It comes at some cost, of course, because if the swing plane is steeper, vertically going up steeper than the ball is falling, then you do have timing mistakes that you can make. If you time it just right, you can hit it well, but if you're a little in front or a little behind, you're going to hit either on top of the ball or on the bottom of the ball. You'll get either a weak pop-up or a weak grounder. So it comes at some cost. So it's almost an all or nothing strategy. But the way to get some information about a batter's swing plane is to look at how his exit velocity on the average depends on the launch angle. And you can see differences among players. Here is Chris Bryant, third baseman for the Cubs, whose father read Ted Williams' book and told him, elevate your swing, okay? And you can see that his swing is such that he gets a maximum exit velocity at about 20 degrees, something like that, which means his swing plane is probably in that neighborhood. Compare with Jose Altuve, who is not really a home run hitter, although he does get his share of home runs. He was the most valuable player last year in the American League, Houston Astros. Again, we're looking at average data here. He swings a much lower swing plane. He is really, basically, Altuve has an on-base swing, okay, and Bryant has a home run swing. So this is sort of how you could, how a batter can use information like this to adjust his swing. All right, I'm going to skip this, and I'm going to skip this because we're really out of time. And I'm going to skip this because I'm out of time. And it's okay. So in conclusion, I've given you lots of examples of how physics enters the game of baseball, and I've only covered a small fraction, and even less of a fraction than I guess as I skipped over stuff. But that's all right. You can ask me questions if you want. I love talking, writing about this stuff, so feel free to contact me or email, my website, Twitter. I tweet about this stuff too. And I want to close by sort of saying that knowing the physics of baseball does not make you a better player. And basically, I'm living proof of that. This is me at the Red Sox fantasy camp from 9 years ago, with my number 9, Ted Williams, okay? And I don't look too bad here, but I don't play that well, and it doesn't help, trust me. Thank you.
Support for Knowledge Stream comes in part from a generous contribution provided by an anonymous donor.